Good morning. I am Hariss, PhD student in the physics of materials, microelectronics, automations, and thermal laboratory. Today, I will present to you part of my thesis work entitled Role of Honeycomb Structure in Improving the Melting Process of a Phase Change Material Inside a Latent Heat Storage Unit. So we start with the plan of this presentation, which is detailed as follows. First of all, I will present a quick introduction on the subject and discuss the main problem of this work. Secondly, I will represent the validation study. After that, I will expose the system and method of calculation proposed in this numerical study. The fourth part will be devoted to the results. And lastly, I will focus on conclusions and perspectives. The storage of thermal energy is considered to be an efficient solution for renewable applications. Generally, thermal energy storage can be achieved in three forms, namely sensitive, latent, and thermochemical. Among these, the latent thermal energy storage system has proven to be the most efficient. From the point of view of higher storage density and storage of thermal energy at a constant temperature. However, the main drawback of latent heat thermal energy storage system is the low thermal conductivity of current PTM. This weakens thermal conductions in these systems, resulting in considerably long energy storage and recovery times. To increase the thermal conductivity of PTM, different studies examine different approaches, including the expansion of the heat transfer zone using thin metal matrix, carbon nanotube, and the use of nanoparticles. To ensure the accuracy of the current numerical approach, the average liquid fraction is verified with the experimental results of Shukahman and Kamkawi. The lauric acid is filled into a rectangular enclosure with an inside dimensions of 120 mm in height and 50 mm in width and depth. The right wall of the cavity is subjected to a constant temperature, while adiabatic boundary conditions are set on the other walls. From this figure, it can be seen that the numerical model is very consistent with the experimental results. To remedy this problem, we carry out a numerical study based on the numerical simulation of the fusion of a phase change material within a rectangular enclosure with a metal matrix, using the ANSYS Fluent software. This study is motivated by the need to better understand the heat transfer during the charging phase of the thermal energy storage system. In addition, we have proposed in parallel a comparative study between the two configurations. We are talking about a rectangular enclosure without and with honeycombs. Both configurations are subjected to the same boundary condition. The bottom wall is subjected to a constant flux density. We impose natural convection on the upper wall, and we assume that vertical walls are isolated. In order to simplify the calculation, a transient two-dimensional model of heat transfer during the PCM melting process was governed by the following general assumptions. First of all, we see that thermophysical properties of PCM are constant. Secondly, the fluid is assimilated to a Newtonian and incompressible fluid, and we neglect convection in the liquid phase due to the great value of the PCM viscosity. We now move on the discussion of the results. The following image represents the evolution of the phase change interface for the two configurations, i.e. configuration with and without honeycomb. First of all, I would like to point out that the colors blue and red represent the condition when the material is completely solid and liquid respectively. We can observe that at this start time between 0 and 500 seconds of the fusion process, the fusion interface starts from bottom to top, near the source. This indicates that in the early stages, heat transfer occurs mainly by conduction. We also note that the evolution of fusion begins with the edges of the core of a honeycomb and propagates towards the middle of the hexagon. After 3000 seconds, all of the PCM was melted, giving a melting fraction of close to 100% for the first configuration, with metal matrix. However, the fraction was still not completed in the second case. The liquid fraction is a typical dimensionless parameter that characterizes the charging characteristics of latent heat storage unit. This figure depicts the variation of liquid fraction for icosane in a rectangular enclosure, with and without honeycomb structure during the melting process. In the early stage, we note that the evolution of liquid fraction is similar and linear for both configurations, and the heat transfer is mainly by conduction. We also note that the increase in the rate of liquid fraction for the latent heat storage unit with the metallic matrix is faster than the unit with the pure PCM. Furthermore, the impregnation of the honeycomb structure makes it possible to reduce the complete melting time by 30%. According to the numerical analysis carried out using ANSYS Fluent, we conclude that the addition of metal matrix allows to increasing and improving the performance of the system. At the moment, we are comparing the use of a metal matrix with other heat transfer enhancement methods. And we also intend to study the effects of tilt angle on the system performance. Thank you for your attention.